Hi everyone. Welcome to my presentation on my work on online induction motor fault diagnostics. And so I start with a big motivation question. What exactly am I dealing with? I'm dealing with induction motors. So these motors are used in mining companies, in water treatment plants, as we see here, and also in Tesla vehicles. So being having such big and widespread uses, the issue is maintenance. There are costs associated with that, up to about 160% of the initial investment. And so how exactly do we do maintenance in a cost-effective manner? There are three types where we can run to break the motor. Okay, and so these motors are lower in value and they run until they fail. We could also do preventative maintenance, and that is basically at certain intervals do some inspection, or there is condition monitoring. A way where we take a motor, collect some data from it, and then process some fault information so that we can classify the motor to be at risk the moment certain components start to fail as a more effective means of maintenance. So that's the overlying objective of this work. And so I start with a brief background regarding these three, modular aspects. Okay, so for data collection, what kind of data collection? We look into the internals of a motor. And so in a motor, we can collect the current data coming out of the stator windings, as we see here, and we can also collect vibration data. And as evidenced by some publications where we have current data collection being done in this laboratory setup, and some vibration data being collected from this other laboratory setup in 2017. And so that's a very brief background on how data is collected in the field as far as publications are concerned. Now, for the processing of the data, typically a big area of research is in the broken rotor bar fault detection. So the rotor bars are within the rotor here, and if there are certain breaks, it would eventually cause the entire motor to fail. How that is typically done in a majority of publications, they have their basis on collecting the data, as we see here, a sinusoidal electrical current data, and then just processing the frequency domain aspect of it, where these sidebands indicate a severity level of the fault, where if we have more of these sidebands, it would indicate a higher rate of failure. However, there are problems to this typical approach, despite it being the basis of many, many publications. As shown in 2011, the same kinds of sidebands can also occur due to the influence of the connected load. Again, in 2016, this influence is demonstrated where we have different gear ratios, and they would show the sidebands in accordance to gear ratios that could be confused with the fault that's trying to be detected. So and then a brief overview of the classification is a system like this, the adaptive neurofuzzy inference system. This is a general picture where the fault information that comes from the processing gets fed into the system, and then the output, its job is to indicate whether or not the motor has a fault or is healthy. And given this very brief background, here's a summary of existing issues that I found based on what is existing. So the biggest issue that I have observed in this work is practical considerations regarding these several things. So in regards to wired system, here's a picture of wired data. This is stuff I've done in the Thunder Bay water treatment plant, where we open up one of the current transformers and collect data with a laptop using wired means. And this is what it looks like in another local big company, Mahan Electric Limited. They do motor maintenance, and they just run their motors like this, and the data collection involves these wires of significant safety, and generally no company actually does this. And so there are basically, because no company actually does it, you'll never see any laptop next to an open current transformer in any plant. You'll never see wired systems collecting data from motors that are coming in weekly. So that is a problem with wired systems. And also, there is a problem with a lack of speed encoder. Many works, they depend on an encoder attached to a shaft to determine the speed of the motor to help them find the fault. We can see very clearly here in Mahan Electric, they have new motors coming in every week. They run the motors freely with nothing connected. So there's no way to know the speed using an encoder-based solution. And likewise, in the water treatment plant, there was these rotors. They're actually underground. For someone to install an encoder, they'd have to dive underwater and install it, and it's basically not done and not practical. And of course, there is a practical consideration of misleading fault signals. If the fault signals themselves are misleading, they're the basis of everything that comes afterwards to determine whether or not the motor has a fault or not has a fundamental flaw in it. So, and in addition, based on my review, the inputs to these artificial intelligence systems is less than straightforward. Exactly how do we translate any result into something compatible with an artificial intelligence system to give us an output? And these traditional systems, they also rely on something called training, where you feed in an input and get an output and compare it to a known answer. And then based on this error, we can propagate it back and update parameters and hopefully get a more accurate output from the system. The problem with that is, in real places, we never know the answer in advance. So how exactly do we handle this kind of problem? And so now I look into the solutions of these issues that I've stated one by one and very briefly. Okay, so for data collection, instead of those wired sensors that basically no company uses, I have wireless smart sensors developed, as we see here, where we have sensing elements with a smart data acquisition system wirelessly transmitting information for fault feature processing and classification. Having a closer look at this simple block shows this kind of diagram where we have a system that involves signal conditioning so that we can ensure the original sensing unit is compatible with an analog to digital converter. Usually it isn't, right? So that's, and then we have a battery power, which influences the design of the analog to digital conversion, the external crystal, which strongly influences the accuracy, and a memory module that allows us to collect data very quickly and a lot of it so that the correct processing can be done for fault detection purposes. So one of the many aspects of the design is shown in the signal conditioning, as we see here. At least one of the critical aspects to make this smart sensor solution actually work. It involves the sensor output, which in my case, it's a current source, essentially, and I have to feed it into a resistor that amplifies the signal and generates a voltage at this point, going through a low-pass filter because I don't want those high-frequency noise, and some biasing because it's a battery-powered system and it needs to stay above 0 volts at all times. And the design of that basically is a balance of impedance where the impedance at this point has to be lower than the impedance at the rest of the circuit to ensure that I have the correct signal generated. And the impedance from the point of view of the analog to digital converter has to be high enough so that the proper charge can be made here so that the analog to digital converter can work correctly. And also, of course, when I'm talking about impedance, it also is influenced by bandwidth, and bandwidth is influenced by my fault detection method. And also the analog to digital converter itself, there are design considerations on the valid number of bits you can use. We can't just go crazy and use a 30-bit ADC and expect to have a meaningful result. The number of bits is restricted based on the battery power that I have available, and also is based on the noise that's inherent in the original sensor itself, and at the same time also influenced by the bandwidth I use for the application. So it's a balancing act between impedance in available voltage, the noise of the transducer, and also the bandwidth. Balancing these things out, I can successfully create a design for smart sensors. So the result of this work shows this as a smart sensor. So this is a sensing element, and we have a motherboard module here and a battery module here. And the internals look like this. It is as per what my diagram here shows, where we have a voltage regulator, an external crystal, SRAM, wireless transmission module, and a microcontroller unit with an analog to digital converter inside it. The receiver looks like this, where internally it is basically wireless part, the microcontroller, and the serial to USB converter, so that I can connect directly to a computer and get the data. Now, how do I validate something like smart sensors? How am I sure I can actually use it for fault detection? The way I validate is I collect the data, like sinusoidal data here, that's very, very slightly amplitude modulated. And if I collect enough data at a high enough frequency resolution, I should see very precise differences in the resulting frequency. So in this case, it's about 0.5 hertz. And that's if I have a precise enough external crystal to give me an accurate result I can use. In comparison, if I did not have a precise enough crystal, the time domain signal would look identical. You cannot tell from that. However, in the frequency domain, at the same frequency resolution, I cannot see these differences. So the results are not precise enough for me to be able to use for fault detection purposes. And so these are things that came about as a result of working on it. Now, with regards to solutions, now I address both the lack of a speed encoder and those misleading fault signals. So in 2015, one author has shown through finite element simulations the magnetic fields of higher frequency components in the electrical current to be very, very concentrated at the stator. And so it justifies that instead of using these sidebands for that broken bar fault detection, we can use these higher frequency components as a way to more accurately determine the fault features. And so my contribution to that is I also, in addition to these higher frequencies, I've generalized to include even more fault features that I can select from and result in higher accuracy, as I will show you in the results. And I also relate it to the rotor frequency and the line current. Rotor frequency can be determined from vibration. The reason being the shaft of that induction motor has a specific notch, and every rotation generates a very strong specific vibration pattern. I can use that to determine the speed of the motor. So that way I can get around the use of an encoder. And of course, the line frequency I can easily get from the electrical current that I collect. And these two things can be made to work together to get an accurate result for fault detection, as I show here. I have current on one side and vibration, and they work hand in hand to help me determine that, say, the rotor frequency is operating in a consistent manner to prove that my current analysis is actually valid. And so I won't go into those details, but a way to validate my results is shown in this test setup, where I have an induction motor and 3 smart sensors collecting current and one for each phase of the current, and one vibration smart sensor which job is to track the rotor speed. Connected to a gearbox, the same gearbox that many publications say cause problems, and a magnetic clutch to adjust the loading of the induction motor. And so that diagram basically looks like this, and we have the vibration sensor mounted onto the induction motor with a magnet, and the current sensor, just using these split core transformers, hook on to the current lines. So the installation is completely non-invasive. No holes needed to be drilled. Nothing needs to be modified. The motor can always be running, and you just need to put on the sensors, and it will start working. Those are one of the problems to be addressed. And I test between a healthy motor and a faulted motor. So this is an example of a faulted motor where the hole is drilled into to create rotor faults. This is drilled by Mahan Electric, the local Thunder Bay company, and compare it with motors that don't have these holes drilled into it to simulate the defect. And so the results are as follows. So firstly, the vibration looks something like this. If I do the frequency domain transformation, I get a very clear, strong frequency, and I go one step ahead and prove that the frequency with time and the associated energy with time is also consistent. So that means throughout my entire sampling, my analysis of the current would be valid. And looking into the current, I have this result here, where I have a decoupled motor tested and a fully loaded motor. Decoupled means the shaft is freely running, nothing connected. And then the fully loaded is where I've have that clutch current set to the max and make this motor work as hard as it is specified to be able to handle. And the result of unloaded free-running shaft looks like this. So under the traditional sideband-based method, we can see a very clear difference between a faulted motor and a healthy motor, the healthy motor being in green and the faulted motor being in purple. And with the existing methods, we have this choice of fault features, and my revised generalized way to determine a broken rotor bar determines these additional choices as fault features. In this case, because there's no connected load, there is absolutely no problems with a traditional sideband-based method. It is very clear. There's no confusion there. However, I have load connected in this other test, and we can see that there starts to be some kind of confusion because of the connected load. We can see some kind of fault indication in the healthy motor, but the results are very consistent with what can be predicted by theory. I predict where the locations of these frequencies, and that's where they occur. Now, it now brings into another problem that has to be solved: inputs. So given these kinds of inputs, how exactly are we going to put that into an artificial intelligence system? Now, my solution to that is the creation of what I call a fault index, a number where if it's very large indicates a more severe fault, and of course close to zero indicating a healthy motor. And it's basically a signal to noise ratio of my results. So I extract features based on a ratio. If I were to base it just on the absolute magnitude, it's meaningless without reference to noise. And if I do a typical, in publications, logarithmic representation in decibels, it becomes a little less meaningless because the difference between the fault feature and the noise are not several orders of magnitude larger. They're just several times larger than the noise. So having a direct ratio more accurately represents the fault features, as I will be showing. So given this fault index, what do the results look like? I compare existing methods with my own. So using the sidebands and creating those corresponding fault indices, I get this result, where we have 3, 2, and 1 bar faults. So basically, rotors with 1, 2, or 3 bars, holes drilled into them to simulate the defect, and it compares against a control group of 2 healthy motors, H1 and H2. And we can see that under some conditions, there's some confusion between a healthy and a faulted motor. And then I compare with the other existing method where there's it does separate the healthy and faulty very well, but however, there is some confusion between a 1 bar and a 2 bar fault here, where 1 bar is supposed to be less severe than one that has 2 holes drilled into the rotor. And then with my proposed method, I do get, it's not perfect, but it at least can more accurately represent the real condition of the motor. And so now that leads to the final practical consideration, training. Artificial intelligence systems generally need training. How do I solve the fact that you can't really train a system where you don't know, because you don't know the answer in advance? This graph here actually is an average of a lot of my data. So I do average so I don't choose the best result. It's just whatever it happens to be. And if I plot out my original data into a graph, it looks like this. So a way to help with classification is to track where these data points are very closely packed together. A measure of this packedness, like this closeness, is with something called potential, where you compare the new incoming data point with all the previous data points in the past. However, there is a problem with something like this. Say we collected data from a place for 10 years. We have 1 billion data points and 1 billion more on the way. It's not practical to keep 1 billion data points for every single motor for forever. So the solution to that is I derived a recursive form of this kind of calculation so that instead of keeping track of 1 billion values, I can keep track of, say, 10 values and still accurately represent the density of that data as if there were 1 billion. The result of that is I was able to identify certain cluster centers, so points where there's a very high data concentration. And also where the location of these are influenced by new data coming in. So that means as I collect new data, say if data is concentrated at this point, then all these other points here, based on this calculation, would reduce in its data potential, indicating that these points of references are becoming less and less relevant as data changes over time. Now, the classification I finally do is based on proximity of the data points with these cluster centers. So if an incoming point, say this healthy point here, is closest to this point, then it would be considered a healthy case. If the data is close to any of these points up here, it is considered a faulted case. So I could achieve an accuracy of up to 100% without any training involved, just due to proximity of the points. It is strictly not 100% because there were certain points that was not able to have a high enough data density to justify some classification. However, practically speaking, I can clearly determine a healthy condition from a faulted condition, which is what actually matters. Now, comparison of my results to a standard ANFIS system, adaptive neural fuzzy inference system, shows this result, where it can achieve a higher accuracy, but at the cost of you having to supply the answers as you train it. So basically, data is being fed into here and compared to an answer that you also give it, and then based on that answer, you update these parameters, and then the subsequent inputs become more and more accurate. So even though it is less accurate than a typical adaptive neural fuzzy system, there are significant disadvantages in practical use because you have to know known answers to the system in terms of being able to classify whether something is faulted or not. I've got 4 minutes. Right. So now, some conclusions. For data collection, from this work, I can conclude that wireless non-invasive low power systems are not necessarily not a bonus, but a necessity, because these are unworkable situations in real life. Even though they work very well in the lab, we do need wireless systems. So it justifies developments of these kinds of sensors. Better fault detection can be accomplished with more types of data collected. I collect vibration data, and it helps me be able to detect faults in a more accurate manner, as I've proven in results. And unsupervised classification needs a careful design of the fault index. So some index that correlates strongly with what we're looking for, what kind of faults. That would be key to a successful unsupervised classification. Now, what exactly is new? That's probably what my supervisor told me you guys will ask me. There's a unique sensor design here that basically isn't exactly in books or from publications. And there's also a more accurate fault detection scheme that I've developed that I've also validated with under zero load free running shaft conditions, which is a condition ignored in most publications, despite it actually being useful for at least one of our local companies. And also, I have developed an unsupervised evolving classifier for use with broken rotor bars in induction motors. I could not find an equivalent publication on that subject. And so that ties into future work where these two aspects here with the sensor and the more accurate fault detection is in a paper publication currently under review. My supervisor hopes to have a patent related to this unique sensor design and an additional paper with regards to this unsupervised evolving classifier. So aside from these things, my obvious future work would be I have to finish that thesis too. And also, with regard to the research itself, what kind of future work is open to a future researcher? The data collection itself is something very open in that it's not just vibration and current. There's magnetic fields, there's radar, there's high-frequency ultrasound, many other applications this technology can be applied with. And the fault detection basis can benefit from a more accurate model. It requires very advanced knowledge of electrical and mechanical aspects. When I looked up the derivation of fault detection techniques, I found that, and it was it hasn't been improved actually in the last 30 years. And more work can be done on providing additional fault indices, which is related to better fault detection, so that better unsupervised classification can be achieved. And last but not least, I'd like to make some acknowledgments to the people that and places that made this thing possible. First, to the Bear Point Water Treatment Plant and the Mahan Electric companies for providing a real-world test environment to validate these new technologies developed. Also to EMEC Systems Incorporated, Dr. Wong's company, and the Sunbest company for helping actually create these the actual physical sensors themselves, and the local hackerspace, home-based hackerspace, for providing a lot of materials I otherwise would have bought, and also from several Lakehead students. These three helping with code, and Rahul teaching me how to create. Do 3D modeling to create these kinds of cases, and Manzar for helping me take pictures. So that is the end of what I have to present. The backup archive of this very presentation is in this link here. Feel free to ask me any questions. Stop recording now.